Hello there, and welcome to the Sleepy Cosmic Lens.
Before the first light broke the darkness, before time had meaning, before even space itself could stretch or bend, there was nothing, or so we believe, yet from that nothing, everything we know was born. The stars, the galaxies, the atoms that build our bodies all emerged from a moment so small, so brief, that the very laws of nature struggle to describe it. But what came before? What existed in that silent pause before creation began? To answer that, we must journey beyond the reach of telescopes, beyond the limits of time itself, into the deepest question ever asked. What was the moment before creation?
To ask the question is human. To stand beneath a canopy of stars, a velvet darkness punctured by the cold ancient light of a billion suns, and to wonder, where did all of this come from? It is a question that has echoed in our minds since the first moment we possessed the capacity for wonder. We have woven answers into our myths, embedded them in our philosophies, and sought them in our equations. And our modern science, our cosmology, has provided an answer of breathtaking scope and detail. It all began. There was a moment, a singular event, some 13.8 billion years ago, from which all of space, all of matter, and all of time erupted into being. We call it the Big Bang. But our minds, shaped by the relentless rhythm of cause and effect, are not so easily satisfied. We hear of a beginning, and we instinctively, immediately ask the next logical question. What came before it? If the universe was born, what was the state of non-existence that preceded it? If there was a cosmic dawn, what was the nature of the night that came before? This is the ultimate inquiry, the question that lies just beyond the horizon of our knowledge. And it is here that we encounter the first great paradox of creation. For when we ask this question of modern cosmology, the answer it gives us is both profoundly simple and impossibly difficult to comprehend. The answer is that there was no before. This is not an evasion. It is not a statement of ignorance. Although it is tied to the limits of our understanding, it is a fundamental consequence of our deepest insights into the nature of reality. In the framework of modern physics, born from the mind of Albert Einstein, the Big Bang was not an explosion that happened at a point in space and at a moment in time. It was the origin of space and time themselves. Time is not an eternal, absolute river that flows independently of the universe. It is a property of the universe. It is a dimension that was born and that has been expanding ever since that first moment. To ask what happened before the Big Bang is a question that folds in on itself, a logical contradiction. It is like asking what is north of the North Pole. Once you are at the pole, the concept of north ceases to have meaning. Every direction is south. Similarly, if time itself began with the universe, the concept of before ceases to have meaning. At that origin point, there is no prior moment on the cosmic timeline, because there was no timeline.
Imagine the entire history of the universe as a book. The Big Bang is the first word on the first page. We can read the story from that first word to the present day, and we can even speculate about how the story will end. But the question, what happened before page 1, is a question that the book itself cannot answer. It is a question that steps outside the story. Before page 1, there is no story. There are no words, no characters, no setting. There is only the potential for a story to be written.
The laws of physics, as we currently understand them, describe the narrative from that first instant onward. They tell us how the plot develops, how the characters, the particles and forces interact, and how the setting, the fabric of space-time evolves. But the very language of our physics, the language of time and space, comes into being on that first page. This idea is deeply unsettling because it runs contrary to every intuition we have. We are creatures that live and breathe in time. Our memories construct the past. Our senses perceive the present, and our hopes and fears shape our imagination of the future. The arrow of time is the most fundamental experience of our consciousness. To be told that this fundamental reality had a beginning is to be told that the stage upon which our entire existence plays out is not eternal. It is a finite, created thing.
And so we struggle. We try to imagine a dark, empty void, a silent, timeless eternity waiting for the universe to be born. But even this imagination is a trap. An empty void is still a space, and waiting is an action that requires the passage of time. Our minds and our language are so deeply embedded within the framework of space-time that we cannot easily conceive of a state in which that framework does not exist.
And so we stand at a precipice. On one side is our human intuition, our relentless need for a cause to precede every effect, a before to precede every beginning. On the other side is the stark, elegant, and deeply challenging picture painted by modern cosmology. A universe that is self-contained, a history that begins with its first moment, a reality where the very concepts of before and eternity must be re-examined. The birth of time and space from the crucible of the Big Bang is not just a scientific theory, it is a philosophical revolution. It forces us to confront the possibility that the universe does not adhere to the narrative logic we try to impose upon it. It challenges us to think beyond our own experience, to stretch our minds to their absolute limits, and to accept that the ultimate answer to our oldest question may not be an answer at all, but a fundamental rethinking of the question itself. The journey to understand what came before creation must, it seems, begin with the acceptance that there may have been no before at all.
To understand why physics leads us to this bewildering conclusion, we must venture back in time, not just for 13.8 billion years, but to the very first instant of that cosmic story. We must journey to a state that lies beyond the reach of our most powerful telescopes, a condition so extreme that it defies all comparison to anything in the universe today. This is the state from which everything we know emerged. We call it the singularity.
The word itself is an admission of the limits of our knowledge. In mathematics, a singularity is a point where a function goes to infinity, where the normal rules break down. In cosmology, it represents a moment in the past when the universe was compressed into a state of infinite density, infinite temperature, and infinite space-time curvature. Let us try for a moment to unpack what this means. Infinite density implies that all the matter and energy of the observable universe, all 100 billion galaxies, each with hundreds of billions of stars, was packed into a region of zero volume, not just a small volume like the head of a pin, but a geometric point with no dimensions at all. Infinite temperature means the energy at this point was limitless, a furnace hotter than the core of any star, hotter than anything we can imagine or create. An infinite space-time curvature means that the very fabric of reality was bent into a shape so extreme that space and time as we know them would have lost their meaning.
This is the picture that emerges when we take Albert Einstein's theory of general relativity, our best description of gravity and the large-scale structure of the universe, and run the clock backwards. We observe that the universe is expanding today. Galaxies are rushing away from each other. If we rewind this cosmic film, we see those galaxies coming closer together. The further back in time we go, the smaller, denser, and hotter the universe becomes. The equations of general relativity predict that if we go all the way back to time zero, we reach this state of infinite values.
But here we must be very careful. Physics does not like infinities. An infinity in an equation is usually a warning sign, a red flag that the theory itself is being pushed beyond its realm of applicability. It signals that we have reached a point where the physics we know ceases to function. The singularity is not a physical object or a place. It is a theoretical boundary. It is the point where general relativity, the science of the very large and massive, breaks down. The problem is that in the conditions of the singularity, the universe was not only infinitely dense, but also infinitesimally small. And the world of the very small is governed by a completely different set of rules, the laws of quantum mechanics. Quantum mechanics is our best theory of matter and energy at the subatomic level. It is a world of probabilities and uncertainties, where particles can be in multiple places at once, and where energy can flicker in and out of existence. General relativity and quantum mechanics are the two great pillars of modern physics. Each has been tested and verified to an astonishing degree of accuracy in its own domain. General relativity perfectly describes the orbits of planets and the bending of light around galaxies. Quantum mechanics perfectly describes the behavior of transistors and the energy levels of atoms. But the singularity is the one place in the universe where both theories must apply simultaneously. It is a place that is both unimaginably massive and subatomically small. And when we try to apply the equations of both theories to this state, they clash. They produce nonsensical answers, infinities that tell us nothing about the physical reality of that moment. It is like trying to describe a single phenomenon using two different, incompatible languages. One language describes the curvature of the stage, the other describes the dance of the actors, but we have no grammar to combine them into a single coherent sentence. The search for this grammar, this unifying theory, is the single greatest challenge in fundamental physics today. It is the quest for a theory of quantum gravity. Such a theory, whether it is string theory, loop quantum gravity, or something else we have not yet dreamed of, would be the ultimate language of reality, capable of describing the universe at all scales, from the quantum foam to the cosmic web. A true theory of quantum gravity would, we hope, resolve the singularity. The infinities would disappear, replaced by finite, though still extreme, values. It would allow us to peer beyond the wall of the Big Bang and understand what that initial state of the universe was truly like. But until we have such a theory, the singularity remains a veil drawn across the beginning of time. It is a point of profound mystery. It represents the breakdown of our known laws of nature, a moment when the concepts of space, time, matter, and energy were fused into a state that we cannot describe or comprehend. It is not the universe as a point of chaos, but perhaps as a point of perfect, unimaginable symmetry, a state where the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were merged into a single unified superforce. It was a universe of ultimate simplicity, a seed of pure potential from which all the complexity we see today would eventually unfold. The singularity is the ultimate expression of the mystery of our origin, a silent testament to it, the fact that our journey of understanding is still far from over. It is the point where our science pauses and our wonder begins anew. The idea that time and space are not absolute but are instead dynamic, interwoven entities that could have a beginning is one of the most profound shifts in the history of human thought. For over 2 centuries, our picture of the universe was shaped by the ideas of Isaac Newton. In Newton's universe, space was a fixed, eternal, 3-dimensional grid, an invisible stage upon which the events of the cosmos played out. Time was an absolute clock ticking at the same rate for everyone and everything, everywhere in the universe, from the beginning of eternity to its end. Space was the container,
and time was the river that flowed through it. But both were independent of the contents of the universe. They were the unchanging backdrop for the drama of physics.
This intuitive, clockwork universe was shattered in the early 20th century by a young patent clerk in Bern, Switzerland. Albert Einstein, through a series of brilliant thought experiments, revolutionized our understanding of reality. He began not with complex mathematics, but with a simple observed fact. The speed of light in a vacuum is constant. It does not matter how fast you are moving towards a light source or away from it, you will always measure its speed to be the same, approximately 300.
This simple fact has staggering consequences. Einstein realized that if the speed of light is absolute, then space and time cannot be. They must be relative. He developed this into his theory of special relativity, which showed that time can slow down and space can contract, depending on your motion. An astronaut traveling near the speed of light would experience time passing much more slowly than someone on Earth. A journey that would seem to be a few years for the astronaut could be centuries for those left behind. Time, Einstein showed, is not a universal clock. Each observer carries their own clock, and its ticking rate depends on their motion. This was a radical departure from the Newtonian worldview, but it was just the beginning. Einstein then spent a decade wrestling with a deeper problem: how to incorporate gravity into this new relative framework. The result was his masterpiece, The Theory of General Relativity, published in... General relativity presents a new and breathtaking picture of gravity. Gravity, Einstein proposed, is not a force that pulls objects across space as Newton had thought. Instead, gravity is the curvature of space and time itself. To understand this, we must stop thinking of space and time as separate entities. Einstein showed that they are inextricably linked, forming a single four-dimensional continuum called space-time. This cosmic fabric is not a passive backdrop. It is an active participant in the universe, and it is shaped by the presence of matter and energy.
The theory can be summarized in a wonderfully simple way. Matter and energy tell space-time how to curve, and the curvature of space-time tells matter how to move. The most common analogy is that of a heavy bowling ball placed on a stretched rubber sheet or a trampoline. The ball creates a deep depression in the sheet. This is analogous to how a massive object, like the sun, curves the space-time around it. If you then roll a smaller marble nearby, it will not travel in a straight line. It will follow the curve in the sheet, spiraling inwards towards the bowling ball. From the marble's perspective, it is moving in a straight line, but its path is dictated by the distorted geometry of the surface it is on.
In the same way, the Earth is not being pulled by the sun, by a mysterious, invisible force. It is simply following the straightest possible path, what's called a geodesic, through the curved space-time created by the sun's mass. Gravity is geometry.
This cosmic fabric is not just a theoretical construct. Its effects are real and measurable. One of the first confirmations of general relativity came from observing the path of starlight passing near the sun during a solar eclipse. The immense mass of the sun warps the space-time around it, and the light from distant stars following this curvature is bent. The stars appear to be in a slightly different position in the sky than they actually are. This phenomenon, known as gravitational lensing, has since become a powerful tool in astronomy, allowing us to map the distribution of mass in the universe and even detect the presence of invisible dark matter.
Even more dramatically, Einstein's theory predicted that this space-time fabric could have ripples. If a massive object is accelerated, it should create disturbances, waves of space-time curvature that propagate outwards at the speed of light. These are gravitational waves. For a century, they remained a purely theoretical prediction too faint to be detected. But in 2015, a century after Einstein published his theory, the LIGO experiment made one of the most stunning discoveries in the history of science.
It detected the faint whisper of gravitational waves from the cataclysmic collision of two black holes over 1 billion light-years away. For the first time, we had directly observed the ringing of the space-time fabric itself.
It is this dynamic, flexible, and very real nature of space-time that leads us to the Big Bang. In 1929, the astronomer Edwin Hubble observed that distant galaxies are all moving away from us, and the further away they are, the faster they are receding. This was the first evidence that the universe is expanding. But what is it that is expanding? It is not that galaxies are flying apart through a pre-existing, static space. It is the space-time fabric itself that is stretching. The galaxies are like raisins in a baking loaf of bread. As the dough expands, it carries the raisins along with it. The distance between every pair of raisins increases, but the raisins themselves are not moving through the dough.
This discovery that space-time is an expanding fabric is the observational foundation of the Big Bang theory. If the fabric of the universe is stretching today, then in the past it must have been smaller. And if we run the cosmic clock all the way back, we arrive at a moment when the fabric was infinitesimally small, a moment when the stretching began. This is the birth of time and space. The Big Bang was not an explosion in space, it was the explosion of space. It was the moment that the cosmic fabric began its relentless, ongoing process of unfurling. This is the universe that Einstein revealed to us, not a static stage, but a dynamic, evolving, and created entity. With the understanding that time and space form a single dynamic fabric that had a beginning, we are forced to confront the profound implications for our oldest question. The query, what happened before the Big Bang, seems simple, even childishly so. It is the question every child asks at the end of a story, and then what happened? Or, but where did the story begin? It is rooted in our fundamental experience of linear time, of a past that gives way to a present that flows into a future. Our minds are narrative machines, constantly constructing stories to make sense of the world. And every story requires a context, a setting, a once upon a time. But the universe, as described by Einstein's relativity, does not appear to follow the rules of a human story. By revealing time to be a dimension, a component of the physical universe, Einstein demoted it from its role as an absolute, external framework. Time is not the narrator of the cosmic story, it is part of the story itself. The pages of the book are not just filled with events, the pages themselves, the very fabric of space-time, are being written as the story unfolds. The Big Bang in this context is the first sentence, and the question, what is written before the first sentence, is a question that misunderstands what a sentence is. It presupposes a page that exists prior to the writing, a timeline that is prior to the events.
This is the linguistic trap that we fall into. Our language is a product of our evolutionary history on this planet, a tool designed to help us navigate a world of medium speeds and medium sizes, a world where time appears to flow at a constant rate and space appears to be a fixed, three-dimensional arena. Our grammar is built upon tenses, past, present, and future. The word before is one of the most fundamental prepositions we have, but we are now using this evolved local language to try and describe a state of reality that is utterly alien to our experience. We are using the language of the riverbank to try and describe the source of the river itself, a source where the very concept of flow may not apply.
Let us return to the analogy of the South Pole. A journey to the South Pole is a journey in a specific direction on the globe. But at the pole itself, the rules of direction change. The framework of longitude and latitude that we use to navigate the globe converges and breaks down. The question, what direction is south of the South Pole, is not a deep mystery. It is a semantic error. It is applying a concept south in a context where its definition is no longer valid.
So, it may be with time, our journey back to the Big Bang is a journey to the South Pole of the timeline of our universe. At that point, the very concept of time, of a before and an after, may undergo a phase transition, changing into something else entirely, something we might call a purely spatial dimension. In this view, the universe did not arise out of a preceding moment, but from a timeless state, just as the surface of the Earth emerges from the South Pole, without there being a surface south of it. This presents a formidable psychological barrier. The idea of an uncaused beginning is deeply unsettling. To our intuition, we are so accustomed to the chain of causality that the idea of a first link in the chain that was not forged by a previous one feels like a violation of logic. It feels incomplete, unsatisfying. It is why the idea of an eternal, cyclical universe has held such appeal throughout human history, as it removes the problem of an absolute beginning. It is why creation myths almost universally posit a pre-existing state, be it a divine being, a cosmic ocean, or a formless chaos. The human mind seems to have a deep-seated need for a temporal precedent. But science is not obligated to satisfy our psychological needs. Its purpose is to describe reality as it is, not as we wish it to be, and the reality described by general relativity is one where time is a physical, contingent property of our universe. The question of what happened before may not make sense, not because the answer is hidden from us, but because the question itself is ill-posed. It is projecting our local, human-scale experience of time onto the cosmic scale, where that experience may not be fundamental. Perhaps the greatest challenge is to separate the concept of beginning from the concept of creation in time. The Big Bang was a beginning, but it may not have been a beginning in time. It may have been the beginning of time. This is a subtle but crucial distinction. It suggests a universe that is self-contained, a reality that does not require a prior state of non-existence from which to emerge. It simply is, and its history is a finite story that starts with its first moment. To truly grasp this, we must perform a difficult act of mental gymnastics. We must try to step outside our own temporal existence and view the universe as a complete four-dimensional object, a block of space-time laid out all at once, with a boundary in the past that is not an edge in a larger timeline, but the natural geometric origin of the object itself. It is a demand that stretches our imagination to its breaking point, and in doing so reveals the profound mystery that lies at the heart of our cosmic story.
And so, we find ourselves at the edge of the known world. We have journeyed back to the dawn of our universe, only to find that the dawn may be a boundary beyond which our science, in its current form, cannot see. The singularity, that point of infinite density and temperature, stands as a formidable barrier, a wall where our most successful theories of the universe, general relativity and quantum mechanics, fall silent. This is not merely a technical problem to be solved with more powerful computers or larger telescopes. It is a fundamental challenge to our understanding of reality.
The origin of the universe is the ultimate mystery, a question that pushes science beyond its traditional limits and into the realm of philosophy and perhaps even art. This mystery is not a cause for despair. On the contrary, it is the lifeblood of science. Science is not a collection of established facts, but a process of inquiry, a method of questioning. It thrives not on what is known, but on the boundary of what is unknown. It is the great unanswered questions that drive progress, that inspire new generations of thinkers, and that force us to invent new mathematics, new technologies, and entirely new ways of seeing the world.
The puzzle of the Big Bang is perhaps the greatest driver of them all. It is the impetus behind the decades-long search for a theory of quantum gravity. It is the reason we build colossal particle accelerators to try and recreate the conditions of the early universe for a fleeting instant. It is the reason we design space telescopes to capture the faintest, most ancient light, seeking clues in the afterglow of creation. The question of what came before is the engine of our curiosity. While general relativity tells us the question may be meaningless, that very conclusion is what pushes us to find a deeper theory that might give it meaning. It forces us to ask, is time truly fundamental, or is it an emergent property of a deeper, timeless reality? Is our universe the only one, or is it part of a grander cosmic multiverse? Was the Big Bang a singular one-time event, or is it part of an endless cycle of cosmic birth and death? These are the questions that are born from the mystery of the singularity. They are the questions that animate the frontiers of theoretical physics today. In this way, the birth of our universe represents more than just a physical event. It represents the point where all our modes of inquiry converge. It is a question for the physicist who seeks the underlying equations. It is a question for the philosopher who ponders the nature of causality and existence. It is a question for the theologian who contemplates the concept of a first cause and a creator. And it is a question for every human being who's ever looked up at the night sky and felt a sense of awe and wonder. The mystery of our origin is a unifying force. It reminds us that for all our differences, we share a common heritage, born from the same cosmic fire. Every atom in our bodies was forged in that primordial furnace, and in the hearts of stars that followed. We are, in the most literal sense, stardust, the children of the cosmos, and we are, as far as we know, the only part of the cosmos that has evolved the ability to look back and reflect upon its own origins. We are the universe's way of knowing itself. This is a profound and humbling realization. We are not separate from the universe, looking in from the outside. We are a part of it. Our consciousness is a product of its laws, and our questions are the universe's own questions. The mystery of what came before is not just a scientific puzzle. It is our own deepest, most personal inquiry into the nature of our own being. And as we stand before this ultimate question, we are pushed beyond the limits of our established knowledge. But this is where the greatest adventure begins. For while our understanding of time and space, born from Einstein's genius, seems to close the door on the past, another great revolution in physics, the strange and paradoxical world of quantum mechanics, may just offer us a way to open it again, to peek behind the veil and glimpse a reality where something can, and perhaps must, arise from nothing. We have journeyed to the absolute limit of our classical understanding of the cosmos. Our exploration of time and space, guided by the brilliant light of Einstein's relativity, has led us to a wall, a singularity at the dawn of time, where our physics breaks down and the very concept of before becomes meaningless. It is a profound and elegant picture, that of a self-contained universe, a finite story with no preceding pages. And yet, our human curiosity, our insatiable need to ask why, urges us to look for a crack in that wall, a way to peer beyond the boundary of the beginning. It seems like an impasse, a final, unanswerable mystery. But the physics of the 20th century was a tale of two revolutions, not just one. While Einstein was rewriting our understanding of the very large, of gravity, galaxies, and the expanding cosmos, Another group of scientific pioneers was delving into the opposite extreme. They were exploring the world of the very small, the realm of the atom and its constituents. And in doing so, they would uncover a set of laws so strange, so counterintuitive, and so powerful that they would shake the very foundations of reality. This was the dawn of quantum mechanics, and within its bizarre and probabilistic rules, we may find the loophole we are searching for, a path that leads us around the wall of the singularity and toward a new understanding of creation itself, an understanding where the universe does not need a before because it can arise from the most perfect and absolute nothing.
Quantum mechanics is the science of the subatomic. It is the language that describes how light and matter behave at the most fundamental level. And it is a language that seems to be utter nonsense when compared to our everyday experience. In our world, a thrown ball follows a single, predictable path. An object is either here or it is there. A wave is a wave, and a particle is a particle. But in the quantum realm, these certainties dissolve.
An electron can be a particle and a wave at the same time. It can exist in a superposition of many different locations at once. Its presence described only by a cloud of probability. It can even perform a feat known as quantum tunneling, spontaneously passing through an energy barrier that it should, by all classical logic, be unable to overcome. The quantum world is not a world of definite, predictable events, but of possibilities, probabilities, and inherent unavoidable uncertainty.
At the very heart of this strangeness lies the Heisenberg uncertainty principle. This is not a statement about the clumsiness of our measurements. It is a fundamental, built-in property of the universe. It states that there are certain pairs of properties that can never be known with perfect precision simultaneously. The more you know about a particle's position, for instance, the less you can know about its momentum, and vice versa. There is a cosmic trade-off, an inherent fuzziness to reality at its smallest scales. But the most crucial pairing for our story is that of energy and time. The uncertainty principle dictates that the energy of a system cannot be known with perfect certainty over a very short interval of time. The shorter the duration, the greater the possible fluctuation in energy. For an infinitesimally brief moment, the energy in any given point in space can fluctuate wildly. This simple, elegant, and deeply strange principle has a consequence so profound, it completely demolishes our classical idea of nothing. We tend to think of empty space, a perfect vacuum, as the ultimate state of nothingness. No matter, no energy, no activity. But quantum mechanics forbids such a state. A vacuum, to be truly empty, would have to have a perfectly defined energy of zero, and it would have to have it for a definite period of time. The uncertainty principle makes this impossible. The energy of the vacuum must fluctuate. Even in the most profound emptiness imaginable, there is a constant, roiling, underlying activity. These are vacuum fluctuations, a ceaseless quantum hum that pervades all of space. The vacuum is not a silent void. It is a sea of shimmering, ghost-like energy. And it is from this quantum ray definition of nothing that the most incredible possibility of all emerges. The possibility of a universe born from an empty void. A creation not from a divine hand or a pre-existing state, but from the inherent and unavoidable restlessness of nothing itself. To truly comprehend the idea of a universe from nothing, we must first complete our re-education on the nature of nothing. Our journey into quantum mechanics has taken us to the threshold of a new understanding. We have left behind the classical idea of a vacuum as a silent, empty stage, and arrived at the quantum picture of a vacuum as a place of ceaseless, shimmering energy a place where the uncertainty principle guarantees a fundamental level of activity. Now we must take the next step and ask, what is the nature of this activity? If the vacuum is not empty, what is it filled with? The answer lies in the most famous equation in all of physics, E men C co. This equation is a statement of equivalence. It tells us that energy and mass are two sides of the same coin. Energy can be converted into matter, and matter into energy. And this is precisely what happens in the quantum vacuum. The energy that momentarily flickers into existence during a vacuum fluctuation can spontaneously transform into matter.
But there is a catch. The creation of matter must obey certain conservation laws. For example, the total electric charge of the universe must remain constant. To create a negatively charged particle like an electron, a positively charged particle must be created at the same time to balance the books. This is where antimatter comes in. For every fundamental particle of matter, there exists an antiparticle with the same mass but opposite charge. The antiparticle of the electron is the positron.
And so, the energy of a vacuum fluctuation can manifest as a pair of particles, a matter particle and its antimatter twin, an electron and a positron, for example, or a quark and an antiquark. These pairs are known as virtual particles. They are called virtual not because they are imaginary, but because their existence is terrifyingly brief. They are born from a borrowing of energy from the vacuum, a loan granted by the uncertainty principle, but this loan must be repaid, and quickly. The shorter the time of the loan, the more energy can be borrowed. So a pair of massive virtual particles might flash into existence, but they must annihilate each other and vanish back into the vacuum almost instantly, returning the energy they borrowed.
The quantum vacuum, this state of nothing, is therefore a seething, effervescent foam of virtual particle-antiparticle pairs, constantly popping into existence and disappearing again in a frantic, subatomic dance. The most profound emptiness we can conceive of is, at its most fundamental level, a chaotic frenzy of creation and annihilation. This may sound like a wild, untestable fantasy, a piece of mathematical fiction, but it is not. The effects of this quantum foam are real, measurable, and have been confirmed by experiment to an astonishing degree of precision. One of the most direct and elegant confirmations is a phenomenon known as the Casimir effect. Imagine taking two perfectly smooth, uncharged metal plates and placing them parallel to each other in a perfect vacuum, separated by a microscopic distance. Classical physics would predict that nothing should happen. They are uncharged and they are in an empty void, but something remarkable does happen. The plates are pushed together by an invisible force. This force is the result of the virtual particles in the quantum vacuum. The vacuum is filled with fluctuations of all possible wavelengths. However, the space between the two plates acts as a resonant cavity. It restricts the kinds of virtual particles that can exist there. Only fluctuations with wavelengths that fit neatly into the gap are permitted. Outside the plates, in the vastness of the surrounding vacuum, there are no such restrictions. All possible wavelengths are allowed. This means that there are more virtual particles, more vacuum fluctuations, pushing on the outside of the plates than there are on the inside. This imbalance creates a net pressure, a tiny but measurable force that pushes the plates together. The Casimir effect is a direct, tangible force from nothing. It is experimental proof that the vacuum is not empty, that it is filled with a sea of latent energy and virtual particles. We see the effects elsewhere too. The Lamb shift, a tiny difference in the energy levels of the hydrogen atom, is explained by the interaction of the atom's electron with the virtual particles of the vacuum.
The magnetic properties of fundamental particles like electrons are also slightly modified by this quantum foam. Our particle accelerators, where we collide particles at enormous energies, are constantly dealing with the effects of this seething vacuum background.
The evidence is overwhelming. Nothing is not nothing. The vacuum is a physical entity in its own right, a dynamic and powerful component of the cosmos. This redefinition is the single most important step in our quest to understand a possible origin of the universe from a state of non-existence. It means that the state before the Big Bang, if we can even use that word, may not have been a state of absolute classical nothingness. It may have been a quantum vacuum, a state with no space, no time, and no matter in the conventional sense, but a state that was still subject to the laws of quantum mechanics, a state that was therefore a seething ocean of potential. And if this quantum vacuum can give birth to fleeting, microscopic pairs of virtual particles, it begs the grandest question of all: could a vacuum fluctuation under the right circumstances have been large enough and stable enough to give birth to an entire universe? Science that describes the behavior of nothing has opened a door to the possibility that everything we see is simply a form of that nothing, transformed and magnified on a cosmic scale. Having redefined nothing, not as a placid void, but as a dynamic quantum vacuum, we can now take the conceptual leap to the origin of everything. If the vacuum is a sea of potential capable of spontaneously producing fleeting pairs of virtual particles, could it be that our entire universe is the result of one such quantum event, writ large? Is it possible that the cosmos we inhabit is a fluctuation that for some reason did not vanish back into the nothingness from which it came? This is the heart of the something from nothing hypothesis, a theory that attempts to provide a natural scientific explanation for the origin of the universe, grounding it in the well-tested if bizarre laws of quantum mechanics. At first glance, the idea seems preposterous. A universe is a vast and energetic place, the creation of 100 billion galaxies, each containing 100 billion stars, would seem to require an unimaginable input of energy. Such an event would surely violate one of the most fundamental laws of physics, the law of conservation of energy, which states that energy cannot be created or destroyed, only changed in form. The creation of the universe would appear to be the most flagrant violation of this law imaginable. But remarkably, this may not be the case. The universe may not have required any energy to be created at all, because the total energy of the cosmos appears to be precisely zero. This startling idea arises from a careful accounting of all the different forms of energy in the universe. On one side of the ledger, we have the positive energy. This includes the mass energy of all the matter in the universe, the incredible amount of energy locked away in stars, gas, and dust. According to E, it also includes the kinetic energy of all of this matter as it moves, and the energy of all the radiation, the light that fills the cosmos. This is a vast, almost incalculable amount of positive energy. But there is another side to the ledger. Gravity, the force that binds the universe together, contributes a form of negative energy. Think of it this way. To pull a satellite away from the Earth's gravitational field, you have to add energy to it. The satellite in orbit has less total energy than one that is free in deep space. It is in a gravitational potential well. The gravitational field itself can therefore be thought of as a repository of negative energy. Every star, every galaxy is a massive source of positive energy. But it also creates a deep well of negative gravitational energy around it. When we perform a cosmic audit, adding up all the positive energy of matter and radiation, and subtracting all the negative energy of gravity, the two numbers appear to cancel each other out almost perfectly. The best measurements from our cosmological observations suggest that the total energy of our universe is consistent with all available data, zero. This is a stunning and profoundly important conclusion. If the net energy of the universe is zero, then its creation from a state of zero energy does not violate the law of conservation of energy. It is, as the physicist Alan Guth famously put it, the ultimate free lunch. The universe could have sprung into existence without any external input of energy or violation of physical law. This opens the door to a specific quantum mechanism for creation, quantum tunneling. In our classical world, a ball sitting in a valley cannot spontaneously appear on the other side of a hill without being given enough energy to roll over the top. The hill is an energy barrier, but in the quantum world, the ball has a small but non-zero probability of simply appearing on the other side, having tunneled through the barrier. We see this happen with particles, like electrons, all the time. It is the principle behind certain types of microscopes and electronic devices.
Physicists like Alexander Vilenkin have proposed that the universe itself may have been born through such a process. Imagine a state of nothingness, a quantum vacuum with no space, time, or matter. As a state of zero energy like the valley, the existence of a tiny, nascent universe could be seen as a state on the other side of an energy hill. Quantum mechanics suggests that there is a finite probability that a universe could spontaneously tunnel from the state of nothing into the state of something. This would not be an event in time, as there is no time in the initial state. It would be a timeless, probabilistic transition, governed by the laws of quantum physics.
The Big Bang would then be the consequence of this tunneling event. The universe would appear fully formed in a hot, dense state, ready to begin its expansion. The question, what caused the Big Bang, is answered not with a preceding event, but with a probabilistic law. The cause is the timeless quantum nature of reality, which allows for such transitions to occur. There is no why, only a what are the odds. And according to these models, the odds are not zero. This is a vision of creation stripped of all external agency. It does not require a creator or a pre-existing reality. The universe is a self-creating entity. Its existence is permitted by the fundamental laws of physics. The laws themselves are held to be the most fundamental thing, the timeless mathematical blueprint. And this blueprint contains within it the possibility for a universe to emerge uncaused from a state of nothingness. It is the ultimate expression of the creative power of the quantum vacuum, a power that can not only bring forth fleeting virtual particles, but can, in a moment of sublime quantum happenstance, bring forth an entire cosmos. The idea of a universe tunneling into existence from a quantum vacuum solves the problem of a first cause. But it immediately presents another problem, one of scale. A universe born from a quantum fluctuation would presumably be of a quantum size, perhaps no larger than a single proton, a space defined by the Planck length, something like 10^3 35 meters. How could such an infinitesimally small seed grow into the vast, sprawling cosmos we see today? A universe stretching for more than 90 billion light-years across. A simple expansion, like a conventional explosion, would not be nearly fast enough or powerful enough. The answer to this puzzle is one of the most important additions to the Big Bang theory in the last half-century, the theory of cosmic inflation. Cosmic inflation proposes that in the very first fraction of a second after its birth, the universe underwent a period of extreme, accelerated, exponential expansion. This was not a normal expansion like the one the universe is undergoing today. It was a hyper-expansion, a runaway process driven by the energy of the vacuum itself, in a very peculiar state. According to the theory, immediately after the universe tunneled into existence, it was dominated by a hypothetical energy field called the inflaton field. This field was in a high-energy state known as a false vacuum. A false vacuum is a metastable state. It's like a ball resting on a high plateau next to a deep valley. It's stable for a moment,
but it's not in its lowest possible energy state, and this false vacuum state, according to the equations of general relativity, would have had a remarkable property. It would have generated a powerful repulsive gravity. Instead of pulling things together, it would have pushed everything apart with unimaginable force.
Beginning at around 1036 seconds after the beginning, this repulsive gravity took hold. It caused the fabric of space itself to stretch at a fantastic rate. The universe began to double in size, and then double again, and again in an astonishingly short period of time. This doubling process may have happened 100 times or more, all before the universe was 10 32 seconds old. In this fleeting instant, a region of space smaller than a proton was stretched to a size larger than a grapefruit, or perhaps even vastly larger.
The expansion was faster than the speed of light. This does not violate Einstein's principle that nothing can travel through space faster than light. It was space itself that was expanding, carrying everything along with it, like dots on the surface of an inflating balloon.
This period of incredible growth is what takes the quantum seed and turns it into a macroscopic universe. It smooths out any initial wrinkles or imperfections, explaining one of the great puzzles of cosmology, the flatness problem. The geometry of our universe appears to be almost perfectly flat, which is a very special and unlikely initial condition. Inflation explains this naturally. Just as the surface of a tiny, crumpled balloon appears very flat to a microscopic ant on its surface after you inflate it to the size of the Earth, inflation takes any initial curvature of the universe and stretches it out so completely that our observable patch of it appears perfectly flat.
Inflation also solves another major puzzle, the horizon problem. When we look at the cosmic microwave background, the afterglow of the Big Bang, we see that it has an incredibly uniform temperature in every direction we look. But in a universe without inflation, regions on opposite sides of the sky would never have had time to be in causal contact, to exchange heat and even out their temperatures. They are too far apart. Inflation solves this by proposing that the entire observable universe we see today originated from a single tiny, causally connected patch before inflation began. This patch was at a uniform temperature, and then inflation stretched it to its current enormous size, preserving that uniformity across the sky.
At the end of this brief, violent epoch, the inflation field finally decayed, like the ball rolling off the plateau into the valley. It settled into its true vacuum, its lowest energy state, the enormous energy that had been locked up in the false vacuum, driving the expansion, was released in a firestorm of particles and radiation. This event is called reheating. It is this moment that flooded the newly vast universe with the hot, dense soup of matter and energy that we traditionally associate with the hot Big Bang.
In this modern picture, inflation is the mechanism that ignites the Big Bang. The quantum fluctuation provided the spark, but inflation was the explosive fuel that turned that spark into a cosmic inferno, creating a universe large enough and smooth enough for stars and galaxies to eventually form. It is the crucial bridge between the quantum mystery of the origin and the grand, evolving cosmos we can observe. With the end of inflation, the universe was born anew. The cold, empty, exponentially expanding space of the inflationary epoch was gone, replaced in an instant by a blistering, incandescent fireball. The reheating process had converted the potential energy of the inflation field into a tangible reality, a seething primordial soup of the most fundamental particles and forces at a temperature of trillions upon trillions of degrees. This was the true beginning of the hot Big Bang phase, the moment from which our observable cosmic history begins to unfold. And in the first few moments of this new era, in a period of time shorter than a single heartbeat, the entire blueprint of our physical reality would be laid down.
The universe at this stage In the first picosecond, that is, the first trillionth of a second, was a state of almost perfect symmetry and simplicity. The four fundamental forces of nature that govern our universe today were not yet distinct. Gravity had likely separated from the other forces at the end of the Planck era, even before inflation. But the other three, the strong nuclear force, which binds atomic nuclei, the weak nuclear force, which governs radioactive decay, and the electromagnetic force, which carries light, were still merged into a single unified grand unified or electro-weak force. The particles that existed, quarks and leptons like electrons, had not yet acquired their distinct masses. It was a universe of undifferentiated, massless particles zipping about at the speed of light, interacting via a single symmetrical force. But as the universe continued to expand, it began to cool. And as it cooled, it went through a series of phase transitions, similar to how steam, as it cools, condenses into water, and water freezes into ice. At each phase transition, the primordial symmetry of the universe was broken, and the laws of physics as we know them began to crystallize out of the chaos. The first major transition occurred as the universe cooled below a critical temperature, causing the strong nuclear force to break away from the electro-weak force. A little later, at about 10 to 12 seconds, another symmetry-breaking event occurred. The electro-weak force itself split into the two distinct forces we are familiar with today, the weak nuclear force and the electromagnetic force. This was a moment of profound significance. It was at this instant, through a mechanism involving another universal energy field called the Higgs field, that fundamental particles acquired their mass. Particles that interacted strongly with the Higgs field became heavy, like the top quark. Particles that interacted weakly became light, like the electron. And particles that did not interact at all, like the photon of light, remained massless. The universe was no longer a symmetrical soup. It now had hierarchy, texture, and substance. As these laws unfolded, the very substance of our world was fighting for its existence. The hot energy of the vacuum was constantly creating pairs of matter and antimatter particles. For a brief period, the universe was a raging battleground where these particles would be created, collide with their antiparticle partners, and annihilate back into pure energy. According to our standard models, matter and antimatter should have been created in perfectly equal amounts. If this had been the case, as the universe cooled, every single particle would have found an antiparticle partner, and the entire cosmos would have annihilated itself into a sea of light, leaving no matter behind. But for a reason that we still do not fully understand, this did not happen. A slight asymmetry crept in. For every billion antimatter particles, it seems there were roughly 1,000,000,001 matter particles. This tiny imbalance, this 1 in a billion preference for matter over antimatter, is the sole reason for our existence. As the universe cooled and the annihilations proceeded, this tiny surplus of matter particles was left over. All the substance of our world, every star, every planet, every living being, is made from the leftover scraps of that great primordial annihilation. The precise cause of this asymmetry, known as baryogenesis, remains one of the greatest unsolved mysteries in physics. By the time the universe was about 1 microsecond old, it had cooled enough for the surviving quarks to bind together in groups of 3, forming the first stable heavy particles, protons and neutrons, the building blocks of atomic nuclei. For the next few minutes, the entire universe was a nuclear reactor. In a process called Big Bang nucleosynthesis, protons and neutrons fused together to form the first
atomic nuclei, primarily hydrogen and helium, in the same rough proportion of 75% to 25% that we observe in the oldest parts of the universe today.
In just a few short minutes, the stage was set. The fleeting, probabilistic spark of a quantum fluctuation had been magnified by inflation into a vast cosmos. The cooling of this cosmos had caused the fundamental laws of physics to crystallize into their present form. The slight asymmetry of these laws had allowed a universe of matter to survive, and the primordial fires had forged the raw atomic ingredients from which all future complexity would be built. The frantic foundational work of creation was complete. The universe was now ready to embark on its long, slow, and patient journey of evolution, a journey that would eventually lead to the formation of galaxies, stars, planets, and on at least one small world, beings who could look back and wonder how it all began. Our journey to the beginning has led us to a startling and profound idea that our entire universe, in all its vastness and complexity, may have arisen from a simple, spontaneous quantum event. A fluctuation in the nothingness, a borrowing of energy from the void, magnified by a period of incandescent expansion into the cosmos we know. This is a powerful and elegant scientific narrative, a story of something from nothing, of existence born from pure potential. It is a universe that does not seem to require a preceding cause, a before in the classical sense. It is a story that begins with its own first chapter. And yet, the human mind, in its relentless quest for understanding, continues to probe. We look at this picture of a quantum birth, and we ask, is that truly the final answer? Is the quantum vacuum from which our universe may have sprung the ultimate bedrock reality? Or is it too part of a larger, grander, and perhaps eternal structure? Is it possible that the Big Bang was not the beginning of everything, but merely the beginning of our chapter, our cosmic age? To ask these questions is to step beyond the standard model of cosmology, beyond the well-tested theories, and into the speculative frontier. We are leaving the maps territory and entering a realm of pure theory, a world guided not by direct observation, but by the elegance of mathematics and the audacity of the human imagination. Here, at the absolute vanguard of theoretical physics, scientists are exploring a number of breathtaking possibilities, each one offering a different vision of what might have preceded our own Big Bang. These are not established facts. They are hypotheses, glimpses into what might lie beyond our cosmic horizon. They are the stories that science tells itself when it pushes up against the ultimate limits of knowledge. Some of these stories speak of an eternal cycle of death and rebirth, a universe that is forever renewing itself. Others paint a picture of our cosmos as a single, lonely bubble in an infinite ocean of other universes, a vast and varied multiverse. Still, others suggest that the Big Bang was not a beginning, but a bounce, a rebound from a previous contracting cosmos. And some of the most exotic theories propose that our universe was born from a cataclysmic collision between two parallel worlds in a higher dimensional reality. To explore these ideas is to journey to the very edge of what we can conceive. It is to grapple with concepts of other dimensions, of parallel realities, and of an eternity that may stretch not just forward into the future, but backward into an infinite past. This is science at its most daring, its most creative, and its most profound. It is the human mind, armed with the language of mathematics, confronting the deepest mystery of all, and daring to imagine the unimaginable. Let us now step into this speculative landscape and explore the leading theories that attempt to describe what might have come before the moment of creation. Of all the ideas that attempt to describe a reality before our Big Bang,
Perhaps the most ancient and intuitively appealing is that of a cyclic universe. It is a concept that resonates deeply with our experience of the natural world. We see cycles everywhere, the rhythm of day and night, the turning of the seasons, the pattern of birth, life, death, and renewal. The idea that the cosmos itself might follow a similar, grander cycle has been a part of human thought for millennia, from the Hindu concept of the yugas and the cosmic breaths of Brahma to the Stoic philosophy of ancient Greece, which taught of a periodic conflagration and rebirth of the world. It is a vision of a universe that is not a singular, linear story, but an eternal, repeating poem.
The first attempts to translate this philosophical idea into a scientific model arose in the 20th century. The prevailing theory was that the fate of the universe was a battle between two opposing forces, the outward momentum of the Big Bang's expansion and the inward pull of gravity from all the matter within the cosmos. If the expansion was fast enough, or if there was not enough matter, the universe would expand forever, growing colder, darker, and emptier. But if there was enough matter, a critical density, then gravity would eventually win. After billions or trillions of years of expanding, the universe would slow to a halt and then begin to collapse back in on itself.
This collapse would be a dramatic and terrifying event, a perfect reversal of the Big Bang. We call it the Big Crunch. In this scenario, the universe's expansion would reverse into a contraction. Galaxies, instead of rushing away from each other, would begin to rush towards each other. The vast voids of space would shrink. Over billions of years, galaxies would begin to merge, their stars colliding in a chaotic firestorm. As the universe grew smaller, it would also grow hotter and denser. The cosmic microwave background radiation, the cold afterglow of the Big Bang, would be compressed and blue shifted, its temperature rising until the sky itself began to glow. First red, then white, then a blinding blue. Eventually, stars would be torn apart, their atoms vaporized. Atomic nuclei would be ripped asunder into a plasma of protons and neutrons. And then those too would be crushed until all the matter and energy of the cosmos collapsed back into a final, infinitely hot, infinitely dense singularity, a mirror image of the one from which it began.
For many years, the crucial question was, what happens then? Could this final singularity be a point of rebirth? Could the universe, like a cosmic phoenix, rise from its own ashes? Could the energy of the Big Crunch somehow trigger a new Big Bang in an event that came to be known as the Big Bounce? If so, then our universe could be just one in an endless series of cycles, stretching infinitely into the past and infinitely into the future. Each cycle might have slightly different properties, or it might be an exact replica of the one before. It was a grand and compelling vision of an eternal, self-sustaining cosmos, a universe that had no need for a beginning.
However, the simple Big Crunch model ran into a number of serious theoretical and observational problems. On the theoretical side, the laws of physics, as we know them, break down at the singularity. It was not clear how a bounce could even occur. The singularity seemed to be a true end. Furthermore, with each cycle of collapse and expansion, the entropy or disorder of the universe would increase. This would mean that each successive cycle would be longer and larger than the one before it. If you trace this back in time, it implies that the cycles would get smaller and shorter, still leading you back to an ultimate beginning. The model seemed unable to escape the very origin it was trying to avoid. But the most devastating blow came from observation. In the late 1990s, astronomers studying distant supernovae made a startling discovery. The expansion of the universe is not slowing down, it is accelerating. A mysterious anti-gravitational force, which we have named dark energy, seems to be embedded in the fabric of space itself, pushing everything apart at an ever-increasing rate. This discovery turned our picture of the universe's fate on its head. It suggests that our cosmos will not recollapse in a big crunch. Instead, it seems destined to expand forever until the galaxies are so far apart that the night sky between them is utterly black, and the universe fades into a cold, dark, and empty eternity. The simple, elegant idea of the big crunch and bounce appeared to be dead. And yet, the concept of a cyclic universe was too powerful to be abandoned. In recent years, it has been reborn in a new and more exotic form, emerging from the cutting edge of theoretical physics, specifically from string theory and M-theory. This new model, championed by physicists like Paul Steinhardt and Neil Turok, does not require the universe to recollapse. Instead, it proposes that the Big Bang itself was not a singularity, but a collision. This theory, sometimes called the ekpyrotic model, posits that our three-dimensional universe is a vast membrane or brain floating within a higher dimensional space, a bulk, and we are not alone. There is another parallel brain universe separated from ours by a microscopic gap in this fourth spatial dimension. For trillions of years, these two brains drift apart, the universe on each brain expanding, cooling, and emptying out, driven by the lingering effects of a previous collision. But a force, a kind of spring-like potential energy that we experience as dark energy, slowly begins to pull the two brains back together. Eventually, after an almost unimaginable stretch of time, they collide. This collision is an event that happens at every point in our universe at once. The immense kinetic energy of the two colliding brains is converted into a firestorm of matter and radiation, instantly creating the hot, dense conditions of a Big Bang. This collision smooths out the universe and creates the tiny density fluctuations that will eventually seed the formation of galaxies, accomplishing the same task as cosmic inflation in the Standard Model. After the collision, the brains bounce and begin to move apart again, starting a new cycle of expansion and cooling. In this breathtaking vision, the Big Bang was not a beginning, it was just the most recent in an infinite series of cosmic collisions. Our universe is eternal, endlessly recycling itself. This model elegantly solves many of the problems of the old Big Crunch theory. It avoids the troublesome singularity, replacing it with a physical, predictable collision. It incorporates dark energy not as a mysterious afterthought, but as the very engine that drives the cycle. And it offers a picture of a cosmos that is truly timeless, a universe that has been pulsing, colliding, and rebirthing for all of eternity. It is a modern revival of an ancient dream, a scientific framework for a universe that lives and breathes. While the cyclic model offers a vision of an eternal past in sequence, another equally compelling idea suggests an eternity that exists in parallel. This is the theory of the multiverse, the concept that our universe is not the only one, but is instead a single member of a vast, perhaps infinite ensemble of other universes. This is not just the stuff of science fiction. It is a serious theoretical possibility that arises naturally from some of our most successful ideas about the early cosmos, most notably the theory of cosmic inflation. As we have seen, inflation was a period of hyper-accelerated expansion in the first moments of our universe's existence. It is the theory that explains how a tiny quantum seed could have grown into our vast cosmos. But a deeper look at the physics of inflation reveals a startling and profound consequence. In many of the leading models, inflation, once it gets started, is very difficult to stop completely. It may end in certain regions, like it did in our own pocket of space-time, but on the whole, it becomes a self-perpetuating eternal process. This is the theory of eternal inflation. To picture this, imagine the source of cosmic energy, the inflaton field, as a vast, churning ocean.
Due to quantum fluctuations, this ocean is in constant motion. In most places, it remains in its high-energy false vacuum state, causing the fabric of space to expand at an exponential superluminal rate forever. This is the metaverse, a sea of space-time that is eternally creating more of itself.
However, at random points within this inflating ocean, a quantum fluctuation can cause the inflaton field to decay. Like a drop of water condensing from steam, it rolls down to its low-energy true vacuum state. When this happens, the inflationary energy is released, creating a hot fireball of matter and radiation, a Big Bang. In this picture, our entire observable universe is just one such bubble that has condensed out of the eternally inflating metaverse. Our Big Bang was the moment our bubble formed.
But outside our bubble, the inflationary ocean continues to churn, and new bubbles are constantly forming, each one giving rise to its own Big Bang and its own vast universe. The space between these bubble universes is itself inflating at a fantastic rate, pushing them apart so quickly that they can never ever interact or communicate with one another. They are island universes, causally disconnected, each one an entire cosmos in its own right.
This is a vision of creation on an unimaginable scale. It suggests that the Big Bang was not a unique event, but a commonplace one, a natural byproduct of a larger, ongoing creative process. It completely reframes our place in reality. The Copernican revolution taught us that our Earth is not the center of the solar system. Later discoveries showed that our Sun is an ordinary star, and our Milky Way an ordinary galaxy. The theory of the multiverse is the final, ultimate demotion. It suggests that our entire universe, the whole of our reality, is just one insignificant bubble in an infinite cosmic ocean.
But the multiverse is more than just a mind-bending picture of reality. It offers a potential solution to one of the deepest and most persistent mysteries in all of science: the fine-tuning problem. When we look at the laws of physics that govern our universe, we find that the fundamental constants of nature, numbers like the strength of gravity, the mass of the electron, or the energy density of the vacuum, appear to be exquisitely miraculously fine-tuned to allow for the existence of complex structures like stars, planets, and life. If you were to change any of these values by even a tiny fraction, the resulting universe would be a sterile and barren place.
For example, if the strong nuclear force, which binds protons and neutrons together in an atomic nucleus, were just a few % weaker, deuterium, a heavy isotope of hydrogen, would not be stable. No elements heavier than hydrogen could form, and the universe would be devoid of the chemical complexity needed for life. If it were a few % stronger, all the hydrogen in the early universe would have fused into helium, leaving no long-lived stars like our Sun to fuel the slow process of evolution. Similarly, if the energy density of the vacuum, our modern-day dark energy, were not fantastically small compared to its predicted value from particle physics, the universe would have either flown apart too quickly for galaxies to form, or collapsed back on itself long ago. The universe seems to be balanced on a knife's edge of improbability. Why is our universe so lucky?
The multiverse, combined with the anthropic principle, provides a startlingly simple, if philosophically challenging, answer. If there is an infinite number of bubble universes being created through eternal inflation, it is plausible that the laws of physics are not the same in all of them. Each time a new bubble universe forms, the process of symmetry breaking could happen in a different way, resulting in different fundamental constants. In this scenario, the vast majority of universes would be stillborn. They would have laws that do not permit any form of complexity. But with an infinite number of universes, it is no longer a matter of probability.
but of statistical certainty, that some universes by pure chance will have the right combination of constants to allow for the formation of stars, galaxies, and conscious observers. We, by definition, must find ourselves living in one of these rare, life-permitting universes, because we could not exist to ask the question in any other. This is the anthropic principle. Our existence acts as a selection filter. The apparent fine-tuning of our universe is not a miracle that points to a cosmic designer or an impossible coincidence. It is a simple selection effect, like a fish marveling at the improbable fact that its world is made of water. We observe our universe to be fine-tuned for life for the same reason we observe ourselves to be on a planet that can support life.
This is a profound and, for some, unsettling idea. It suggests that the elegant laws of our cosmos are not the only possible laws, but are merely the local, accidental bylaws of our particular cosmic bubble. It replaces a single, unique, and perhaps purposeful universe with a vast, impersonal, and random collection of realities.
The multiverse theory is, at present, untestable and therefore sits at the very edge of science. But it is a direct, logical consequence of our most successful theory of the early universe. It is a vision of creation that is chaotic, profligate, and unending. A cosmic landscape of infinite variety where every possibility is realized somewhere, and our own existence is but a single fleeting note in an eternal symphony of creation.
The theories of the cyclic universe and the inflationary multiverse offer grand, sweeping narratives about what might have existed before our Big Bang. They are top-down approaches, born from cosmological principles, but there is another, bottom-up approach to the problem of origins, one that comes not from looking at the universe as a whole, but from trying to understand the fundamental nature of space and time itself at the smallest possible scales. This is the theory of loop quantum gravity, and it offers a unique and compelling picture of a big bounce, a universe that preceded our own, born not from extra dimensions or colliding brains, but from the very quantum graininess of reality.
Loop quantum gravity, as its name suggests, is an attempt to build a theory of quantum gravity. It is a direct competitor to string theory, but it takes a very different philosophical approach. While string theory starts with the particles and forces of nature and finds that its mathematics requires extra dimensions and a host of exotic ingredients, loop quantum gravity starts with Einstein's theory of general relativity itself and tries to quantize it directly using the established principles of quantum mechanics. It asks, what would the fabric of space-time look like if it too obeyed the fuzzy probabilistic rules of the quantum world?
The answer it provides is revolutionary. In loop quantum gravity, space-time is not the smooth, continuous, infinitely divisible fabric that Einstein envisioned. Instead, at the most fundamental level, at the incredibly tiny scale of the Planck length, about 10⁻35 meters, space-time is granular. It is pixelated. It is woven from a network of finite, indivisible loops, or atoms, of space-time. You cannot have a smaller distance than the Planck length, nor a shorter duration than the Planck time. The smooth continuum of our reality is an illusion, an emergent property of this underlying, discrete quantum structure. Just as the smooth image on a television screen is an emergent property of a grid of discrete pixels.
This fundamental graininess of space and time has a profound consequence for the origin of our universe. It completely forbids the existence of a singularity. In classical general relativity, the Big Bang singularity is a point of zero volume and infinite density. But in loop quantum gravity, you cannot compress the universe to a point of zero volume because there is a minimum possible volume, a fundamental atom of space. You cannot have infinite density because the energy density of the universe has a maximum possible value determined by the Planck scale.
So what happens when we use the equations of loop quantum gravity to run the clock backwards? As we approach the Big Bang, the universe gets smaller and hotter, just as in the Standard Model. But instead of collapsing into an infinitely dense singularity, it reaches a point of maximum but finite density, a state where the universe is compressed to its absolute quantum limit. At this point, the quantum properties of space-time itself take over. Gravity, which has been overwhelmingly attractive throughout the collapse, suddenly becomes powerfully repulsive. This quantum repulsion is so strong that it overwhelms the collapse, causing the universe to rebound. This event is the Big Bounce. It is a natural, predictable consequence of the quantum nature of space-time.
The Big Bang, in this theory, was not a beginning from nothing, but a violent rebound from a previous contracting phase of the universe. This immediately implies that there was a before. Our universe arose from the ashes of a predecessor, a cosmos that existed before the bounce. The equations of loop quantum gravity even allow physicists to model what this predecessor universe might have been like. In the simplest models, it appears to have been a near mirror image of our own expanding universe, a cosmos that was collapsing in on itself, governed by the same laws of physics.
Loop quantum gravity provides a concrete, physical mechanism for a cyclic-like universe, but one that is very different from the brane collision model. It does not require speculative extra dimensions. It is built directly from the principles of general relativity and quantum mechanics. It solves the singularity problem at its core by revealing a new quantum force that arises only in the most extreme conditions. It paints a picture of a universe that is truly eternal, undergoing an endless series of contractions and bounces, with each bounce being a new Big Bang that resets the cosmic clock and launches a new era of expansion and evolution. The theory is still a work in progress, and it faces its own set of significant mathematical and conceptual challenges, but it offers a tantalizingly self-contained and elegant vision of our origins. It suggests that the answer to what came before the Big Bang lies not in other universes or other dimensions, but in the very texture of our own reality. It implies that if we could probe the structure of space and time deeply enough, we would find that it is not a smooth and featureless void, but a vibrant quantum network, a fabric woven from finite loops. And it is the fundamental nature of this fabric that prevents the universe from ever destroying itself in a singularity, ensuring instead that it will always bounce back, that every end is just the prelude to a new beginning. Of all the theoretical frameworks that attempt to describe a world before the Big Bang, none is more ambitious, more mathematically complex, or more mind-altering than string theory. Born from attempts to understand the strong nuclear force in the 1960s, it has since evolved into our leading candidate for a theory of everything, a single unified description of all the forces and particles of nature, including gravity. And in its modern incarnation, known as M-theory, it has produced a cosmological vision as rich and strange as any creation myth. A vision where our universe is but a shadow of a higher dimensional reality, and our Big Bang was the result of a gentle, yet universe-creating collision in this hidden realm.
The fundamental premise of string theory is a radical departure from all previous physics. It proposes that the elementary constituents of the universe are not point-like particles, as we have long assumed. Instead, at the most fundamental level, everything is made of tiny one-dimensional vibrating filaments of energy called strings. An electron is not a point, but a string vibrating in a particular pattern. A quark is a string vibrating in a different pattern. A photon, the particle of light, is yet another vibration. All the rich diversity of particles we see in the universe is nothing more than the different notes that can be played on these fundamental cumic strings. It is a vision of ultimate elegance, a cosmic symphony where all of reality is woven from the music of these tiny vibrating strands.
This beautiful idea, however, comes at a cost. For the mathematics of string theory to be consistent, it requires that the universe possess more spatial dimensions than the three we are familiar with: length, width, and height. Most versions of the theory require a total of 10 or 11 space-time dimensions, one dimension of time plus 9 or 10 dimensions of space. This immediately raises the question, where are these extra dimensions? The proposed answer is that they are compactified, curled up into tiny, intricate shapes on a scale far too small for us to perceive directly. At every single point in our familiar three-dimensional space, there exists a tiny, hidden 6 or 7-dimensional space, a complex geometrical landscape known as a Calabi-Yar manifold. The precise shape of these hidden dimensions is crucial, as it determines the vibrational patterns of the strings and therefore dictates the laws of physics, the masses of particles and the constants of nature in our universe. It is within this higher dimensional framework that M-theory gives rise to a new and radical cosmological model. In this picture, our entire three-dimensional universe is just a subspace, a vast but limited membrane, or brain, floating within the full higher dimensional reality, the bulk. And our brain may not be the only one. There could be other parallel brain universes, perhaps just a microscopic distance away from us, in the fourth spatial dimension.
This is the setting for the ekpyrotic, or brain collision model of the universe, a theory we touched upon in our discussion of cyclic universes, but which deserves a closer look. In this scenario, the Big Bang was not the chaotic singular beginning of the standard model. Instead, it was the result of a collision between two of these parallel brain worlds.
The theory proposes a before state, a cold, empty, and nearly static universe. Two brains existing in this state for an eternity are slowly pulled together by a force acting between them through the bulk. The collision, when it finally happens, is not like a car crash. It is a soft, gentle event that occurs across the entire infinite expanse of the brains simultaneously. As the two brains make contact, the enormous amount of potential and kinetic energy stored in them is released, instantly transformed into the hot, dense plasma of quarks, gluons, and other particles that we associate with the Big Bang. The collision is so uniform that it creates a universe that is incredibly smooth and flat, just as we observe, without the need for a separate period of cosmic inflation. The tiny quantum ripples on the surface of the brains before the collision are imprinted onto the post-collision universe, becoming the seeds for the large-scale structure of galaxies. After the collision, the brains pass through each other and begin to move apart again, and the universe on our brain begins the long process of expansion and cooling that we have observed for the last 13.8 billion years. In some versions of this model, this is a one-time event, the collision that created our cosmos. In other versions, as we have discussed, it is a cyclical process, with the brains destined to collide again trillions of years in the future. This vision of creation is profoundly different from the standard Big Bang. It replaces the mysterious, physics-defying singularity with a tangible, predictable physical event. It offers a natural explanation for the smoothness and structure of our universe, and it paints a picture of a reality that is far larger and more complex than we ever imagined. A world of hidden dimensions and parallel universes.
String theory is far from a proven and tested theory. It operates in a mathematical realm that is currently beyond our ability to probe experimentally. But it is a testament to the power of theoretical physics to generate new and startling pictures of our origins, suggesting that the birth of our entire cosmos might have been just a gentle touch in the dark, a whisper of a collision in a silent, higher dimensional eternity.
We have ventured far into the unknown. We have journeyed through landscapes of thought that push the boundaries of science and strain the limits of human language. We have explored the possibility of an eternal, cyclical cosmos forever dying and being reborn. We have contemplated our universe as a single bubble in an infinite, effervescent multiverse. We have dived into the very fabric of space-time to witness a big bounce born from its quantum graininess, and we have soared into higher dimensions to imagine a universe created by the collision of parallel worlds. These are the stories that science tells when it confronts the ultimate question of what came before. It is crucial now to pause and remember where we are. We are standing on the speculative frontier. The theories we have discussed, the cyclic model, the multiverse, loop quantum gravity, and string theory, are not established facts. They are not, in the strictest sense, fully formed scientific theories. They are hypotheses, mathematical frameworks, and philosophical exploration. They currently lie beyond our ability to test or falsify the traditional hallmarks of the scientific method. There is no experiment we can currently perform that would tell us if there are other dimensions or if our universe is part of a multiverse. These ideas are born not from data, but from a desire to push our existing theories, general relativity and quantum mechanics, beyond their breaking points, to see what logical possibilities they allow. This is physics in a speculative mode. It is a world of blackboards and equations, of thought experiments and computer simulations. It is a search guided by principles of mathematical consistency, elegance, and beauty. The physicists who work on these ideas are like cartographers of the unknown, drawing maps of possible realities based on the clues and whispers they find hidden in their equations. They are following the logic of our most successful theories to their ultimate conclusions, and in doing so they are sketching out the possible shapes that a final unified theory of physics might take. These ideas are glimpses beyond our cosmic horizon. Our observable universe is vast, but it is finite. We can see no further than the distance that light has had time to travel since the Big Bang. This is our cosmic horizon, and we are fundamentally limited to observing what lies within it. These theories are attempts to imagine what might lie beyond that horizon, not just in space but in time, and perhaps in other dimensions. They are the product of our refusal to accept that our knowledge must end where our vision ends. And so we must hold these ideas with a sense of both excitement and humility. Excitement because they represent the sheer, unbridled power of the human intellect to conceive of realities so far removed from our own experience. They are a testament to our enduring, species-defining curiosity. But humility because we must acknowledge that these beautiful, intricate, and compelling stories may be nothing more than that, stories. They may be elegant mathematical dreams that have no counterpart in physical reality, or one of them might be the correct description of our ultimate origins, a truth that we may one day be able to confirm, or the true nature of what came before may be something stranger still, something we do not yet even have the language or the mathematics to describe.
What is certain is that the quest will continue. The mystery of our origin is the most powerful engine for scientific discovery we have. It is what fuels our passion for exploration, our drive to build ever more powerful tools, and our courage to ask ever deeper questions. These speculative theories are the signposts that mark the edge of our knowledge, pointing the way forward into the great, beautiful unknown.
We have come to the end of our great odyssey. We have journeyed across the entire expanse of cosmic time, from the familiar shores of our own world to the fiery, primordial dawn of the universe. We have navigated the elegant, curving geometries of space-time and plunged into the strange, probabilistic depths of the quantum realm. We have stood on the speculative frontiers of modern physics, gazing out at visions of eternal cycles, infinite multiverses, and crashing worlds in higher dimensions. We have sought to answer the oldest and most profound question ever asked: what came before everything began?
And now, having traveled to the absolute limit of our knowledge,
we must confront the final humbling truth. The moment before creation, the ultimate origin, may forever remain hidden from us. This is perhaps the most difficult conclusion for a curious species to accept. We are, by our very nature, explorers, problem solvers, and storytellers. We have an innate drive to know, to understand, to complete the map, and to finish the story. The idea that there might be a fundamental, permanent boundary to our knowledge, a final veil that we can never draw back, can feel like a deep disappointment, even a failure.
But it is not. It is, in fact, the most honest and perhaps the most important realization of our entire journey. To understand why, we must understand the very nature of the veil that separates us from that first moment. The Big Bang itself forms a horizon in time. The conditions of the early universe, that state of near-infinite temperature and density, act as a barrier, a wall of fire that prevents us from directly seeing anything that may have come before. Any information, any structure, any trace of a prior existence would have been utterly obliterated in the crucible of that primordial state. Our universe, in a sense, was born with a memory wiped clean. We can use the laws of physics to trace the story back to that moment with astonishing confidence. But at the moment itself, our laws break down, and the chain of evidence is irrevocably severed.
This is a practical, physical barrier. But there may be a barrier that is even more fundamental. As we have discussed, if time and space themselves began with the Big Bang, then the very concept of before is a logical contradiction. The veil is not just hiding a prior scene in the play. The play itself may begin with the raising of the curtain. In this case, the moment before creation is hidden, not because we lack the tools to see it, but because there is literally nothing to see. The question itself, born from our time-bound language and intuition, dissolves into meaninglessness when applied to a timeless origin. The search for what came before would be like an explorer on a sphere searching for the edge of the world. The journey would be infinite, but the destination would never be found, because it does not exist.
And even in the speculative theories that do offer a before, that prior reality may be forever inaccessible to us. If our universe is a bubble in a multiverse, the other bubbles are, by the very nature of eternal inflation, causally disconnected from us. We can never reach them, never receive a signal from them, never confirm their existence. If our universe was born from the bounce of a prior contracting cosmos, the bounce itself may have been so violent as to destroy all the particular details of that former universe, leaving only the barest imprint of its existence. We are like amnesics, awakening in a world full of evidence of our past since the moment we awoke, but with no memory and no way of ever recovering the memory of who we were or what world we lived in before that moment. To accept this is to embrace a profound scientific and philosophical humility. It is to acknowledge that we are not, and may never be, the masters of the cosmos, capable of knowing all its secrets. We are a part of the cosmos, finite beings with a finite perspective, and there may be truths that are forever beyond our grasp. This is not a cause for despair. It is a cause for awe. A universe that is entirely knowable, a cosmos that could be completely wrapped up and explained in a final equation, might be a tidy and satisfying thing. But it would also be a dead thing. It would lack the one quality that has driven our entire intellectual and spiritual journey, the quality of mystery. It is the mystery of the unknown that gives our quest its meaning. It is the darkness beyond the edge of the campfire that makes the light of our knowledge so precious. The fact that the moment before creation may be forever hidden is what makes our glimpses of cosmic history so breathtakingly beautiful. It is what elevates science from a mere collection of facts into a grand and noble adventure. It forces us to be creative, to be imaginative, to be audacious in our thinking, It is the engine that has produced the very theories we have explored: the multiverse, the cyclic universe, the Big Bounce. These ideas were born from our refusal to be stopped by the veil, from our determination to use the power of our minds to imagine what might lie on the other side. And so we must learn to live with this eternal question, not as a problem to be solved, but as a constant companion, a source of wonder that can never run dry. The hiddenness of our origin does not diminish the story of our universe. It gives it a sacred, mythical quality. Our cosmos is a story that begins in an impenetrable mystery, and it is in that mystery that we find the space for awe, for philosophy, for art, and for a deep and abiding reverence for the vast, beautiful, and ultimately unknowable reality into which we have been born. The final answer may be forever out of reach, but the eternal question will forever be our guide, leading us onward into an ever deeper appreciation of the great cosmic drama in which we are privileged to play a part. And so we are left standing before a veil of impenetrable mystery. But our journey has taught us to question the very nature of the nothingness that we imagine lies behind it. The classical vision of nothing is one of absolute absence, a barren, static void. It is this vision that makes the idea of a universe emerging from it seem so paradoxical, so much like a magic trick. But the greatest revolution of 20th century physics was its radical redefinition of this concept. The quantum vacuum, we have learned, is not empty. It is not a state of absence. It is a state of pure, seething potential. Perhaps, then, the state before creation was not nothingness in the sense of a void. Perhaps it was a nothingness in the sense of a perfect, undifferentiated unity, a state of infinite potential that had not yet chosen a form. Perhaps it was a silence, not of absence, but of a sound that contained all possible sounds within it. Perhaps it was a darkness, not of blindness, but of a light so unified and so brilliant that it had not yet fractured into the spectrum of colors we call reality. Let us think of it as a block of flawless, uncarved marble. The block itself is a thing of substance, but it contains within it the potential for every sculpture ever conceived. It is the David, and it is the thinker, and it is a million other forms, all held in a state of perfect, latent unity. The creation of a sculpture is not a creation from nothing, but a giving of form to a pre-existing potential. The act of creation is an act of symmetry breaking, of choosing one form out of an infinity of possibilities. So it may have been with the universe. The state before may have been this uncarved block, this quantum vacuum, a state of perfect symmetry and infinite potential, containing within it the blueprints for every possible universe, every possible set of physical laws. The Big Bang was the first strike of the cosmic chisel, the first symmetry-breaking event that selected one of these possibilities and allowed it to become real. This is a nothingness that was never truly empty. It was only waiting to become. But what does it mean to wait in a state where time does not exist? This is the final paradox our language presents. Waiting implies a duration, a passage of moments, but a timeless state does not have moments. The waiting of the quantum vacuum was not a temporal process. It was a condition of its very being. It was a timeless, pregnant latency. Its potential for existence was not something that developed over time. It was an inherent, eternal property of its nature. Imagine a single, perfect, unplucked string on a cosmic instrument. Its silence is not an emptiness. It is a state that contains all music, the potential for every melody, every harmony, Every symphony is encoded in its tension, its length, its very substance. It is not waiting to be plucked. Its potential is a timeless fact of its existence. The Big Bang was the first note, a resonant pluck that shattered the perfect silence and began the cosmic symphony, a symphony whose music is still unfolding, its vibrations still shaping the evolution of the cosmos.
This vision transforms our understanding of creation. The universe is not a fluke, an unlikely accident in an otherwise empty void. It is a natural, perhaps even inevitable, expression of the latent potential of a fundamental reality. The laws of quantum mechanics, which govern this potential, may be the most fundamental aspect of existence. And if these laws contain within them the possibility for a universe to emerge, then perhaps the emergence of a universe is what this state of nothingness does. Perhaps the promise of everything was not just a passive potential, but an active, inherent imperative.
This is a universe that is not an intruder in a state of non-being, but a fulfillment of it. It is the sculpture emerging from the stone, the music from the silence, the story from the unwritten page. The line between nothingness and creation is not a hard, impenetrable wall. It is a shimmering, permeable membrane, a phase transition where the latent becomes manifest, where the potential becomes actual. Before the universe was born, there was a state of perfect, timeless, and complete potential. A silence that held all sound, a darkness that held all light, a nothingness that was, and had always been, pregnant with the promise of everything.
And so we arrive at the end of our story. But the beginning of our understanding, we have journeyed back to the dawn of time and peered beyond into the realm of the eternal question. We have seen that the moment before creation may be forever hidden, a final mystery that defines the limits of our knowledge. We have learned to see the nothingness from which we came not as an empty void, but as a vibrant state of pure potential, a silence that held the promise of everything.
Now we must turn our gaze from the distant past and look inward to see how this grand cosmic story connects to our own immediate personal reality. For the most profound truth of all is that this is not a story about a distant, abstract event. It is the story of us. Every atom in your body, every particle of matter that makes you who you are, is a direct, unbroken link to that first fiery moment of creation. Consider a single atom of carbon in the cells of your hand. Its story did not begin with your birth, or with the birth of our planet. Its journey began in the heart of a star, billions of years ago, a star far more massive than our sun lived and died. In its final moments, in the unimaginable heat and pressure of a supernova explosion, it fused lighter elements together to create that carbon atom, along with atoms of oxygen, nitrogen, and iron. That explosion scattered these precious, life-giving elements across the galaxy, seeding a vast cloud of gas and dust.
That cloud, over millions of years, drawn together by the patient, relentless force of gravity, began to collapse. At its center, a new star was born, our sun. And in the swirling disk of material that surrounded it, that single carbon atom found itself caught, colliding with other atoms, sticking together to form grains of dust, then pebbles, then rocks, then a planet. It was buried deep within the molten earth, and then brought to the surface through volcanic activity. It was part of the atmosphere, then absorbed by an ancient plant through photosynthesis. It became part of that plant which was eaten by an animal, and so on through the great chain of life, for millions of years, until it became part of the food you ate, and was incorporated into your very being. But the journey does not even begin with that first star.
The hydrogen atoms that fueled that star were themselves forged in the first few minutes after the Big Bang. They are pristine relics from the dawn of time, and the quarks and electrons that make up those atoms were born from the pure energy of the reheating after cosmic inflation, and that energy was released from the decay of the inflaton field, which itself was a quantum fluctuation that drove the hyper-expansion of a universe that may have tunneled into existence from a timeless quantum void. This is your cosmic lineage. It is an unbroken chain of causation that stretches back 13.8 billion years from the flesh and blood of your present existence to the first spark of creation. You are not a visitor in the universe. You are the universe. The cosmos is not something external to you, a spectacle to be observed from a distance. It is your own extended body, your ancestral home. The laws of physics that guided the formation of galaxies and the burning of stars are the same laws that govern the firing of the neurons in your brain and the beating of your heart.
Think of this the next time you take a breath. The oxygen you draw in was forged in a star. The nitrogen that makes up most of the air was forged in another. You are breathing in the remnants of stellar explosions. With every breath, you are taking the cosmos into yourself. And with every exhalation, you are giving yourself back to the cosmos. This simple, unconscious act is a constant, rhythmic reminder of your intimate, inseparable connection to the whole of reality.
And what of the consciousness that experiences this? What of the mind that is capable of tracing this story, of feeling awe at its grandeur? In a universe that began as a mindless burst of energy, in a cosmos that evolved for billions of years through blind, impersonal physical processes, a part of that universe has now woken up. Here on this small planet, the universe has evolved the capacity to be aware of itself. Your thoughts are not just your thoughts. They are the universe's thoughts. Your questions are the universe's questions about itself. Your sense of wonder is the universe experiencing its own magnificence. We are the living evidence that creation is not a static one-time event that happened long ago. It is an ongoing process, an unfolding story, and we are at its cutting edge. The journey from the first spark to the formation of stars and galaxies was the universe developing its structure. The journey from the first life on Earth to the complexity of the human brain was the universe developing its consciousness. And our quest for knowledge, our relentless drive to understand the story of our origins, is the universe completing a great and beautiful circle, from a silent, unknowable beginning to a mind that can finally ask and appreciate the question of what it all means. Before the universe was born, there was silence, and within that silence, the promise of everything. Good night.